we can get started. And let's jump into where we left off things last time. So as a reminder, okay, so I was saying, I want to kind of just take a moment that we remember where we are and what are we learning and why are we learning it. I know we are all tired. It's almost the end of the semester. So we are at a phase where we are talking about one of the three main stages of the LLM development pipeline. And we have weeks back have talked about pre-training, which was self-supervised learning using language modeling objective to learn vast knowledge that is available from massive amounts of the data. Then we have learned recently about supervised fine-tuning, and this was introduced to have our models be capable of following instructions. They kind of have all this knowledge, but they're not so far used to following what we explicitly say to do. And then last time we have talked about reinforcement learning from human feedback or alignment, where we're talking about the stage where we make chatbots based on large language models useful assistants by having them be more aligned with human values. Of course, that's a very loaded term, what is a human value, but in general, it is like not aiding illegal activities, not being explicitly hateful, and so on. And how does this fit into an NLP course? Well, understanding this pipeline matters because you have already seen that we can use large language models, even those that we have developed years back, to develop solutions for many applications, including machine translation, summarization, classification, question answering, retrieval, and so on, right? So these models are becoming a useful tools for many applications. So if you know how they are developed, if you are aware there is a pre-training stage, there is a instructional fine-tuning stage where we use lots of human label data, you have a better mental model of what these models are, and with the mental model, you can use them better as well, right? For example, if someone says, well, large language models have learned how to summarize text out of thin air, you would say, well, not really. There is a supervised fine-tuning stage where we have given lots of summarization data, and this is where the models acquire this skill. It's not just out of language modeling and vast amounts of data. Many of you, not everyone here, but most of you are CS majors. And my position is that also you need to go a step further and understand algorithms that can induce certain behavior, right? So last time you have learned about RLHF. So now you know an algorithm for how to induce following instructions while also not aiding with illegal activities and being spread out hateful. So this is just a moment where we kind of take a step where we rethink where we are. So we are learning about the alignment. We are learning a lot about alignment because LLMs are our Swiss knife for many NLP applications. And we just need to understand how that part is actually developed to have a better mental model of how to use them. And some of you in future might build new generation of these models too. Okay, so to continue where we left things off, last time you learned about PPO, right? And I have shared on Friday a documentation of my notes that is basically what you have heard from me last time. But these notes are, whenever I feel like there is more math and whiteboard, I also like to, give you notes just because I feel like this is a more structured way to present it. So if you haven't seen the notes I sent on Friday, please do check them out. I think they are helpful. But as a kind of recap of PPO, I will go over these notes. So first of all, pre-training and supervised fine-tuning precede alignment, right? And now, after this course, you have this nice technical language to talk about things. So I say, pre-training is just a collection of online metadata. It's a sequence, it's a set of sequences of tokens, right? And we train our transformer-based model. Here we are using this notation pi to refer to a model by using as inputs our snippets of text shifted by one position to the right, because we started with this BOS token. And our ground truth outputs, what we deem that should be produced by a model, is the actual sequence, right? So you have seen this multiple times in practicum, in homework, in the lectures. And our loss is always negative log likelihood training, because here we are trying to produce as many tokens there are in the snippets. We are going to take the sum or the average of negative log probabilities at every decoding position. And what is really important for me, and you have seen this 1 million times by now, is that this token here refers to the ground truth token, right? We are producing we are trying to minimize negative log probability of truth, which is a thing that should have appeared. So this is going to be the actual token. Okay, so you have seen this many, many times. And then we had this supervised fine-tuning stage. And here what has changed is what is the data? Data is not just a script of input anymore. The data is some input, some prompt, such as summarize this text and then a document, together with what is a desirable response, which, high quality data doesn't just lay around. So here we have actual human annotators who can often produce these responses. Our objective is kind of the same. Again, we are decoding our response, right? One position at a time, next on the prediction, right? We are, again, taking negative log probabilities. And here, the supervision comes from the fact that we have this human written, typically, although it can be also generated, response. And again, we are trying to minimize negative log probability of the thing that has to appear, ground truth. So this token, RJI, is not any token. It is the J token in the actual human written response. And its probability is what we are trying to maximize. And now, last time we have talked about reward models and PPO. And now the kind of data we have has changed slightly, right? Instead of just having a sequence of text or prompt and a response, now we actually have generated responses and some person's preference for which one of these responses is better. So here we have input, prompt, X. We have some winning response and we have some losing response, right? And again, this is where human annotated data comes into play. When ChatGPT was released, I have heard a lot of news articles along the lines, oh my God, this chatbot has just learned to do all of this out of the internet. And that was the mistake. It was a factually wrong statement, because you know how much human written responses there are in the instruction fine-tuning data. And you also know that this preference data comes from people giving preferences. So it's not that the model had emerged, this skill emerged, we actually taught it this skill. Okay, so our reward model was just a transformer-based model, and our head was a regression head, right? So here, W refers to our vector of the dimension of the size of our hidden representations, and we got a one scalar score out of this equation, right? So this is just one scalar saying what's the quality of the response. And as our loss, we said, well, we know that there is a winning and there is a losing response. And we want the score of the winning one to be much higher than from the losing response. So why not maximizing the difference of the scores we give to these two things, which is written by their difference, right? So if we maximize the difference, we can minimize the log probability of the difference too. So that's how we train our reward. And then the last thing we talked about last time, this is still everything I'm saying is just a recap of the things we have said last time, nothing new here, is how to actually additionally fine-tune our instruction fine-tune model to be a helpful and harmless assistant using these rewards. And here we said we have two objectives. One is to maximize the reward for responses our model is generating. So here it's important, and this is something I haven't emphasized so much last time, so I want to emphasize it a lot, is that this response comes from the model that we are currently fine-tuning further, okay? So it generates something, we use our reward model to give it a reward, and then we want to maximize this reward, which I think is quite intuitive, right? You want to fine-tune your model to have responses that are as high of the quality judged by the reward model. At the same time, we said, well, we don't want the reward, our current model to kind of go too far away from the SFT model we started with. And one reason is because the reward model was trained with the outputs from the SFT model. So when I go back to this data was created by taking the responses from the SFT model, and then a person says which one they prefer. So now your reward model was trained by seeing a response and giving it a score. If now these responses are widely different pieces of text, it's going to become confused because we know that machine learning models struggle with generalization. So that's one reason why we have killed divergence over there. And the other reason I mentioned last time is that policy model, that the one that we are fine-tuning in this last stage, can notice somehow that if we produce a certain words, that the reward is becoming high. And this is called reward hacking. And then it produces gibberish text of the kind I have shown you at the end of the last lecture. Oh. Okay, so we have these two objectives, and we have combined them under a single objective. Here, you need to kind of have in mind what is an expectation and what is the equation for K divergence to see how we get this combination and why a certain term drops. I made a note about that below. I have written here some additional notes for you. I won't go into them into the lecture, but this is all about how we actually compute the K divergence. So that's where we stopped last time. Again, if you haven't looked into these notes, oh no, please check them out. But today we are going to continue. This is just a little snippet to kind of show you how simple using PPO in practice actually is, right? Because bless them, Hugging Face did everything for us, right? So we don't need to write most of these equations or anything. We need to have our SFT model. We need to get responses from the SFT model. So these are 2 lines of code. Then given our responses, we need to give them reward. Just call our reward model on these responses. And then we have PPO trainer class written for us, and we are just taking a step of our PPO trainer optimization. So although everything I said in those notes looks scary, potentially, I don't know, here using PPO in practice is pretty simple. And all this said now, I'm going to make you very mad for a moment. I will tell you that we have shifted from reward models and PPO to something called direct preference optimization, or DPO. And the most appealing property of DPO is that we have ditched our reward model. So now we are going to do everything we have done with the reward model and PPO. I see the faces. Don't be too mad. I promise you that understanding PPO will help you understand DPO. So why did this happen? First of all, RLHF has this complex three-stage pipeline. You have instruction fine-tuning, then you have training a reward model, then you have PPO, right? And if you have taken any RL reinforcement learning classes, probably your instructor had told you that training RL is really unstable, and there are all these tricks to make it work. So if we can avoid reinforcement learning, we certainly would like to do that because the training is going to be simpler. So what DPO folks have done late 2023 is just we looked really deeply into these equations and realized you can change them a little bit, reparameterize them, and then the need for the reward model will disappear, and we'll see how exactly. You will still need the preference data. You will still need a prompt to at least 2 responses and preference for which one is better. And today, when you read any reports that actually report how they train their LLMs, DPO is used over PPO. Okay, so we are still going hard on this course, I know. There will be 2 or 3 slides with a bunch of equations. I decided not to write them on the board because they're so long, it's going to take me too long of a time to actually write them down. But I will stop and see whether you would prefer that I write something on the board. So let's start. And then please stop me if there is anything unclear. The first equation we see at the top, this is just the combined objective for training PPO, as I have shown you last time and just now, right? We are trying to maximize the expected reward and minimize the KL divergence. And combined way for writing that is that equation at the top. Now, I won't derive this. This comes from, if you read the DPO paper, you will see they have followed a bunch of prior work to say that this optimization problem has a closed form solution, meaning we can produce an equation for a perfect language model, perfect policy. P star here refers to an optimal language model, the language model whose weights will maximize that expectation above. And it's given by this formula that includes this term ZX over here. And a thing with ZX is that if we need to marginalize over all possible responses, which we really don't want to. That's language is infinite, so this becomes a problematic. Okay, so you have a closed form solution. You have to trust that all the prior knowledge that this is truly the solution to the optimization problem above. What these authors of this DPO trick have done, they have rewritten this equation such that the R star is on the left side. So you just, multiply by ZX and, do some arithmetics here, simple stuff to have R star being on the left side. So these two are, equivalent. You're just changing what's on the left side. Okay, so this says that the reward for a perfect model that maximizes the expectation of our combined objective has the following reward. Okay. Was that clear so far? Is it clear that where did the first equation came from? Is it?
Yeah, to be clear, we could replace in the second equation the RXY. We could put the star there. But we don't, just for simplicity.
Where exactly would you put it? Sorry, I didn't quite get that.
In the second equation for pi star.
Uh-huh.
Or one above.
Uh-huh. Here?
Yes.
So here?
Yes.
Yeah, I guess, yeah.
It could be R star.
Yeah, that's right. Yeah.
But it's fine.
Yeah. Okay. So started with the combined objective, trusting the prior work that this has a closed form solution, rewriting that equation to have the reward under the optimal solution. Okay, so now I rewrote the first equation again. This is what was in the previous slide. And now in the second, this red box, I have written what we have talked about last time, which is this key piece of our loss for the reward model, right? We said we want to maximize the difference of the score we give for the winning response relative to the losing response. And we can write that with just their difference. And then using a little bit probabilistic notion, we will add sigmoid as well, right? And if we write out what a sigmoid is, remember, sigmoid of z equals 1 plus e2 minus z, right? Then I get this part, right? So this is nothing else than using my definition of the sigmoid function and plugging in what the input to the sigmoid is, which is this difference, right? And therefore it's there. The difference is negated and appears as the superscript over E. This and this are equal things, right? That's a little bit of math. And for example, you can multiply numerator and denominator with the this term, and then this will appear from factoring these things below. So that's just a little bit of simple math. So this is our likelihood that the winning response is preferred under our reward model than right? Like we can define it like that. Is that clear? This is as well, this red box is repeating what we have seen last time, but I want to make sure we are okay with that definition. Yeah, okay, great. And now we can plug in here into this equation over here. We can plug in this equation, right? So what I'm getting in this line over here is this bit with this placed for the reward. Okay. I'll just let you kind of look into it a little bit, right? So notice how we have this here, and now, okay, this looks kind of the same at here. Power 2 is basically this equation. And then instead of I, we place the winning response, and the losing response, okay? You have a question?
That was what I was wondering.
Yeah.
Was replacing those y values. I see it now.
Yeah, because here we have winning, losing, and here I is unspecified. Here we can put winning, losing.
Okay.
Yeah.
So
I feel like you are still looking into them. Is it clear though? Yeah. Clear on this side. Okay, cool. You can see now why I didn't want to write on the whiteboard. It would take a long time. So now, again, with a little bit of math, you can get the next equation. So let me see what I wrote here. How do we get it exactly? We're going to, as far as I remember. Okay, we want to factor out this part. You see how beta times logarithm of z of x appears everywhere, right? And we also know this equation. Right, this is familiar. So what we have here is e to the power of a plus b. So we know we can factor it out like this. And that means that in both numerator and denominator, we can have a term e to the power of beta logarithm of z of x can be factored out, right? We see that. Would you rather me writing this on the board though? No? I'm fine either way. It's up to you.
So in this case, okay, so the numerator,
Mm-hmm.
we could say, given that formula here, we could say that A would be something like beta log and then that fraction.
Mm-hmm.
And then
Yeah.
B would be beta log ZX. So you could do,
Mm-hmm.
you could break up that exponential that's adding those things up there
Yeah.
into two separate exponentials that you're multiplying together.
Yeah, exactly.
Okay.
We did that, and then crucial piece to notice is that this term over here appears both in the numerator and denominator. We see that?
Yeah.
Right. Okay, so now, because it appears in the numerator and denominator, it's the common factor, and I can cancel, right? Okay, I have canceled something that includes zeta x, which had a terrible marginalization, right, over all of the responses, which is sweet because that was computationally very, very, very expensive. So now, just through some a little bit of math, I have got rid of the zeta x, and that's the key property here. Okay, so I get rid of it. I still didn't get to this form. To this form, I get by, and I do feel like it would be useful to actually write. Okay, I'll write a little bit. Okay, so we have okay, I won't write these two. That's annoying. So, okay. Times beta log of C of x, and here. I'll just write winning, winning, losing, losing to keep track of that. Winning, winning. Okay, so this is just me factoring out this term. So I can do this, right? And then I can divide both the numerator and denominator with this term, e beta log of winning, winning. If I divide both, that's not doing anything, right? Okay. So now when I divide this term by the exact same term, I'm going to end up with 1 here, right? When I divide this term by its exact same term, I'm going to end up with 1 here. And here, I'm going to have this beta log with losing, losing divided with this term, which includes beta log winning, winning, right? And then here, I can use this property that E, right? We know this as well. So when I use this one, I will get this term over here, right? Do we see that? Okay, cool. And now, this is again bringing us back to the sigmoid definition I have just removed, right? So here, this is 1 over 1 plus e to, let's say, minus z. Okay, then negative of this is z, which goes as input to my sigmoid function. So here I just flip this and I get the sigmoid function called properly, which is great. We do like sigmoid at the end. So let's go over key things that had happened here. The key thing that had happened is canceling this guy, because this is where my zeta function is, that includes marginalizing over all possible responses in a language, which are infinite many of. And then with a little bit more of math, I get the sigmoid. So now I can have my negative log over this and expectation to get my equation for loss, for training my final model such that it's a helpful and harmless assistant using preference data. So we are having we are minimizing the negative log of this sigmoid we have created. And basically what this sigmoid is doing, it's again almost like that difference between the reward for the positive and negative, right? So again, we have this difference of some things for the winning and something for the losing. However, here, we are not just using the probability of that winning response, right? It is also including that tail divergence, that the probability itself shouldn't stray too far from the reference. Here, I'm following the notation in the DPO paper. They refer to the SFT model as the reference. So once again, if you ignore ignore these for a moment, right? What is this? And I actually want to emphasize what this is. I wrote it in the notes. But I kind of haven't made that super explicit. When we write this notation, we are actually referring to what is the probability of this response constrained on a given input under this model, right? And we all know that the probability of a sequence is given by the probability product of probabilities, right? So this symbol here refers to all the tokens before the jth token in the response. Let's say there is m of them, right? And we also know that this probability for us is given through softmax. Softmax is for us a vector of the size of the vocabulary, right? And we are looking at a probability for certain token. I should write this differently. Let me write it like this. So I need the position in the softmax vector where the vocab ID of this token ij is, right? So if this token was, let's say, word tomorrow, and tomorrow had token 3, I would index my softmax by finding the third position in the softmax. And then again, remember logits we get by projecting the some hidden representation onto the sides of the vocab. These are all the things you have seen many times. So, but just maybe you are not aware of this formulation, like pi refers to a model, and when we write pi of I given x, what we mean is what is the probability of this response I constrained by x under this model, and it comes from this product of probabilities, which are product of certain values in the softmax. Okay, so going back to what we have here, if you ignore the denominators for a moment, basically we are saying, I want the probability of the winning response to be higher under my model than it is the probability of the losing response. And that's great, because if the probability of the winning one is higher, then it's going to be generated more often than the losing one. And now the denominators serve only to keep the probabilities still somewhat close to the SFT reference model, right? So we are doing two things at the same time. Yeah.
So which model is this pi theta in this case? Since now we're only using a reference, since we're trying to avoid using a reward model, the denominator is obviously that reference model.
Yeah, SFT.
The SFT. What is this theta model then if we're not using a reward model?
Yeah, so that's something we called the pi RL last time. That's the copy of the SFT model we are now fine-tuning with this final alignment step.
Okay.
Right, so there is our reference SFT model, and then we have called it, I think, pi RL theta.
Oh, I see.
Right?
Yeah, I see.
So that's, remember, we have a copy of SFT to save it for reference, but then we have a copy that we are now fine-tuning further in this third stage of development. Right, so don't forget there is a whole language model we are training here. And then you're right, previously we also had the reward model, which we no longer have. Yeah. Yeah, lots of models to keep around. So that's why my notes that I sent and shared again at the beginning of the class, I paid a lot of attention to kind of mention all of these model versions. Okay, so this is an equation we use to train and find the final weights in the final fine-tuning stage using a DPO from the preference data. The nice thing about when DPO was released, you can see these graphs here. We have different sampling temperatures for when we choose which tokens to display. And the win rate means that a certain model, like PPO, had won over some other model. I don't remember which one here exactly. Point here is that the higher the win rate, the better the model is. And you can see here that when we compare DPO and PPO, so those are going to be yellow and pink lines, that in many cases, all cases, for all sampling temperatures, DPO is better than PPO. It's also the case here. And what we can see is that if we sample, if a temperature is moved all the way to the 1, the DPO doesn't break as much as PPO does, which means that it's more stable. And this is why today it's a more common algorithm to use to do this final stage of tuning. Again, just a snippet that shows how you can use these equations and put them together. This is not from Hugging Face. This is actually from the original author code. I've been using Connor slides here. Today you will have DPO in Hugging Face as well, but Connor was presenting this basically when DPO was released. Okay, I want to move towards some challenges that we face with alignment today, but I want to make sure that you do not have any questions related to this equation. Yes?
Do the preferences have to come from SFT generations, or can we use other existing preferences?
So you have, let's say, you have reference data that comes from, I would say, LAM, and you want to use it to train another model, let's say, Quen. I'm not 100% sure, but I would be very surprised no one is using them or using them just for a single model. So my, kind of intuitive response would be you can use it probably for other models, but I'm not convinced.
Okay, thank you.
It just feels weird that you couldn't reuse them. Yeah.
Confused because this is like sort of online, right? Thinking in the probability of the model that you're training, thinking in the probability of the
Okay.
strategy is.
Oh, no, here it's about the preference data information. It is what is a winning and what is a losing response, right? So you can still place that model and get what the probabilities of that model would be, right? Like you just look into softmax. You don't care what the model would actually respond. You just poke into the softmax values. Yeah, sorry.
Just to reiterate, where do we actually get this this pi theta, this to be final language model? Does it start as like a copy of our SFT model?
Yes.
And then we, do the necessary training.
Yeah, that's right.
fine-tuning?
So you can imagine you have your SFT model. It has its matrices. There are certain numbers. There are weights in them, right? And you just copy that model, and that's your starting point, right? Like your initialization, let's say.
Right.
And then you are changing those weights further using this equation that's here, right? Like you want to, here it's expectation, but we are going to sample certain responses out of the model. And then we are going to compute this equation, and that's going to be our loss. And we are going to, again, take the step of the optimizer and so on.
And when we're doing that, I see that we are referring to that reference model, but we want to keep that SFT reference model fixed.
Yeah, that's right. Yeah,
Okay.
of course, yeah, because you want to, you want to be having your probability similarly to what the actual SFT model would be. So you will have to copy, like this is your SFT model, and then you make a copy of it, and that one becomes this pi RL, but it's changing, right? It's not going to stay copy of SFT.
Right, the PyRL one is going to change, and then that reference model that we have, we want to keep that fixed as we're training the PyRL.
Yeah, so basically this is a copy and this one is fixed.
Got it.
Okay, yeah, I mean, for sure, these are a little bit more advanced stuff, and RL is never gentle on your brain, in my experience. But I hope the general themes are clear here. So I'm going to go over some challenges, not every single one of them, but few. So one thing to know about RLHF is that, by the way, we are still in the community referring to this reinforcement learning from human feedback. Even though we are using DPO and there is no reinforcement learning, it kind of also became a standalone term for, oh, we are doing alignment. So this is our phase. When you're training model with this preference data, it has been shown that models will have exhibit what you say less of the instance time, where the model is explicitly saying a stereotype or something hidden. So if you report how many times your model has said something explicitly, let's say toxic about here women, it will say less so than its instruction fine-tuning version or the base version. However, when we look at the generations and lots of generations, and we see then how many times women have been mentioned, we will also observe that the model stopped mentioning women altogether. So kind of to avoid the instance harm, he started to produce what we call distribution of harm, where the model across many generations, across this distribution, is not representing the population well enough. And this is hard to fix. We have already talked about the problem of hallucinations when AI makes something up which contradicts our knowledge or doesn't exist in the real world. And people have observed that hallucinations can become worse with RLHF. Then we have these two things. Have you ever experienced that an LLM just refuses to tell you something which you deem to be benign? Ever had that experience? Not really? Okay, I mean, this is less so these days. In 2023, it was really hard to balance them being harmless while also assisting you when you needed help. They would go a little bit more in the direction of just refusing. So this problem known refusal had been a thing that people have, needed to fix. And it still can be a problem when you mention something very, very simple, benign, and the model doesn't want to address it. Now, there is a big discussion about what are human values, right? Like we are trying to align with human values, but there are so many different cultures around the world and so many different ethnicities. So whose values? What do we mean by values? There is a big discussion around that. And also the noisiness in the preference they find themselves, because just because I prefer one output, it doesn't mean that another person prefers them too. And this has been measured with these are early data sets with preference data. People have noticed that if you have multiple annotators for a single pair, that there is a big disagreement with them. So what do you do then? That's kind of a noise, right? And what is the real preference? So there's something else people in this space are doing. The way we test for alignment is called red teaming. So you produce a model, and then developers of this model recruit other people to red team the model, meaning they try to stress test it, they try to see any kinds of way to break the model, to say something explicitly illegal or harmful, which would mean that they broke the alignment. And then whatever these group of annotators have discovered, developers take that information into account again and maybe repeat or do additional process of alignment, iterate over this until they feel like breaking the alignment is too hard, and then they feel they can release the model. This was breaking a model was more a thing, I would say 2023, 2024. I would say it's really hard today to break the models in silly ways. There are still ways to break them. These include like, oh, people will notice if you give your prompt in another very low resource language, you can break the alignment because the model is not super accustomed to that language, and all sorts of tricks. So you can probably see the one with like, oh, my grandma would read me about the nuclear war and she taught me how to build this chemical, but I just forgot the detail and I miss my grandma so much, and like this kind of give the model into giving you the output you wanted. So there are all these funny ways to break them. There is a website, bummer, I remember to show it to you, where you can try to, it's like a game, you try to break the alignment phase, and it became really, really hard. At least for me, I don't know, I'm not so creative when it comes to breaking models. Okay, so there are many more challenges related to alignment here. I have shared a very extensive article about it. So if you are interested, you should definitely check it out. But it's a huge topic on its own. Professor Daniel Brown is also researching this, so he's also a great person to talk more about this. Yeah.
So you mentioned that hallucinations become more common,
Yeah.
like DPO and everything. Is there any link between like the quality of the preference labels that we're giving and the hallucinations? Because I've imagined if we have like gold standard, like human preferences,
Yeah.
like that were written out by human maybe.
Yeah.
Let's say there's like some misinformation, some reason in that, we're training a model on that preference, that we would start to say, like, okay, like, even though this is maybe like that preference, like, we still prefer this over this. And the gold standard is like some sort of misinformation, like, is there any link between that?
Not the one that I would know of. Maybe someone did make this connection, but yeah, I haven't seen it. I don't think that's the cause. I can't really fully explain my argument here. But I do think it always comes down to basically with this final stage of alignment, you are shifting the distribution, right, over the lookup. So we had for a given position previously, you would output something based on some distribution. And now, because you're telling the model, watch out for saying, if not explicit, but through these preferences, the signal, oh, your reward might become bad for this, and this is tied to certain tokens, like, imagine explicitly root tokens become suppressed on this distribution. So now I don't know how this shifts in probability distribution caused this, but I think it's more something about that rather than data itself mentioning something. Although you're right, like their responses, who knows what they mention, right? Yeah, that. Yeah, that's right. So yeah, now I'm rambling and thinking out loud. I'm kind of disagreeing with myself, but yeah, you're right that if you had so for example, one of the things we don't want models to do is to say misinformation, and especially conspiracy theories. So if someone had prompts that kind of are trying to elicit model being sycophantic and agree with conspiracy theory, then you would have that in preference data. But then again, we have trained the model to not lie those responses, so I don't know why you would hallucinate more. When we are telling it this is bad, right?
Yeah. You might have covered this, but how is like the sampling for the preferences actually happening? So it's taking, like, how's the actual preference sampling occurring? Are we taking like a cross product, I guess? Are you taking for every like example, we take every other one and get?
Oh, from the pair?
Yeah, like how do you actually choose different?
We just use different temperatures to sample and on different responses.
Okay.
So you have reasonable temperature, which can give you a more reasonable response. And you have, lower temperature, and it becomes totally crazy. There's always option of, we hear it say winning or losing, but actual options are this one is better, this one is worse, what are terrible, what are good. So in the actual preference data, maybe you have lots of these that what are bad, but we would discard those sometimes, Yeah.
Sorry, I also mentioned the ordering of fines, and it's not like catastrophic forgetting after some stages. Was curious, like if you change the pipeline, with the human preferences, like what kind of different happened in this?
Yeah, so this relates to something else. I think this is my other thing I wanna talk, okay. Yeah, yeah, I will answer your question because we are going to talk about like how does the pipeline for training LLMs looks today, and then this curriculum comes into play. We'll cover that and then I can see whether you have additional questions. Okay, I see lots of people are popping out, so it seems like a little break wouldn't be too bad. So let's take 2-3 minutes break and then we'll continue.
Why is it? Or no, when is it? That I don't know also about it, but. Yes. Okay. I didn't find that. That's amazing. That's actually good. But, weird way, it's like. Yeah, it's on, it's like, you know, it should go good at the same thing, but. Should have raised the hand, that, That's really good. Yeah. Well, this is the binary search thing is also. At the end of the talk, I just thought of it. I can do that. Yeah, I did it. He said that he thought that she wants to put up students, whatever. Yeah, boy, you brought it up even after, but yeah. It was like, no, it's like, typically, like, I was pretty, I'm trying, I remember you mentioning it, and I remember reading it, but still slightly being, but now I can't remember the context at all. Yeah, so, basically. Think about how we were not like, that's a very exciting state of but if we move that, without that people, pretty. Very cool. And then wait, how that works? Any, so. Yeah, wait.
Okay, let's continue. So good news, we have finally covered all 3 stages of the LLM development. This exact information we can learn how to do pre-training, instructional fine-tuning, and RLHF with DPO was how ChatGPT, when it was released in 2023, was developed. And since then, these 3 major stages still remain 3 major stages. With some additional tricks that have been introduced into each one of them. I shouldn't say tricks, rather advances. That sounds more substantial because it is. And then today, this last stage with RLHF has also been used to, instead of producing harmless responses, it has also is used for producing responses that are better for more complex tasks that require more complex reasoning. And since it seems like today I'm kind of on time miraculously for the first time ever, I think I can talk a little bit more about it. So good news, we kind of know what large language models are, and let's just look into a little bit more, modern flavors of each one of these three stages. This is just another schematic of these stages. So you have, pre-training and then post-training referring to instruction fine-tuning on LHF. And then there are different, since 2023, there have been different specializations that have happened. One of them we have learned about previously, which is retrieval augmented generation. When you take your LLM and you also have your database and you are retrieving from a database and then adding that to the input to an LLM. You have probably have seen like web agents, all sorts of agents, coding agents, multimodal LLMs, and so on. And one very prominent theme these days is to build reasoning models. How many of you have heard about DeepSeek R1? You raise your hand if you have. Great, yeah. It's very interesting to see to me how you know very recent stuff. It's definitely, the field is so popular. So reasoning language models, one of them, DeepSeek R1, has been very prominent. OpenAI's O1 is another prominent one, and there are many more today. And why reasoning? So let me give you an example. Here is, my husband is teaching analysis, and I'm like, give me one example I can show. And luckily, immediately, the first one was where I can make this illustration, where at the top we have instant ChatGPT, which is basically the ChatGPT you get using this pipeline I have just covered, right, with pre-training, instruction, fine-tuning, and RLHF. And here is this thinking or reasoning language model, which has another stage of development. I will tell you how it works in a moment. What is special about reasoning language models is that they produce very long pieces of text that we refer to like thinking tokens, which is not a great word because it kind of imposes that they are doing something human-like, but that's, something that the community is using. So you can see thought for 39 seconds, and these are thinking traces. ChatGPT will show you a summary of the whole thinking traces, but they are way longer in under the hub that we can't see. And when the model has this additional capacity to generate many more tokens and then arrive to its answers, it improves its ability to solve complex tasks. So here the answer was correct. And in the instant version of ChatGPT, it was wrong. So that's nice, right? Like we know how to go about producing better model versions that can answer more complex reasoning phenomena. Again, hold on for how exactly. Why reasoning? Okay, obviously there are some useful cases. As I said, this is a question that someone in an analysis class had, so maybe at home they had the same question. And, it would be great if the student had actually had correct answer, right, rather than wrong. Right? Actually, if you see those two chats side by side, I know the answer, but like it's really hard to, if you don't know the answer, to say that the wrong one is wrong, because it still gives you some derivations. It still sounds smart in a way, right? So, yeah, there are real needs. But in the grand scheme of things, not everyone is asking coding and math questions. So how come that the community, this is 2025, how many papers there are on reasoning language models? This paper had estimated there are 60,000 research papers on reasoning language models in 2025. What is it? Just by February? Very short period. This is a word cloud that the organizers of our conference on language modeling. It's a new but very popular conference. So they've taken all the papers published at Column and they have generated this word cloud. And you can see that reasoning has been the most popular word in research publication at the top conference on language modeling. So first of all, what is reasoning? In AI, terms have they're very overloaded, right? So reasoning can mean actually many things, but how we use it in our AI community in 2025 is to refer to the ability to answer questions that involve complex process with intermediate, multiple intermediate steps, and that the model can actually verbalize its thinking about those steps. And why that has it gained such a dramatic attention? Well, foremost, it's challenging, right? But it's foundational. Ability to reason is necessary for planning and decision making. So it's a foundational challenge. And it is somewhat promising. So the interest started with chain of thought prompting. Remember, chain of thought prompting is a simple idea to add, let's think step by step to the prompt, and then the model verbalizes its reasoning and gives the answer. And in that paper, they have shown that by doing that, the model is better at tasks such as mathematical problems and coding. And that kind of kicked off this new era of trying to improve that because people have seen some promise. Okay, now I'm going to tell you how reasoning language models come about. But for that, actually, I want to refer to latest open weight language model that has been released, which is almost 3. And I want to come to it because I want you to I taught you how these 3 stages had worked, but this was in 2023, right? So what has changed in this recent 2 years? So we are going to click at each one of these, and then here you can read what it's referring to. So pre-training, of course, it's still there. We use the unlabeled data, mostly coming from the web. But then there is that curriculum that we have mentioned. So they are referring to this final stage of pre-training with unlabeled data, where you change the source of the data to be targeted to something. They refer to it as mid-training. It's nothing different than pre-training. You still have language modeling objectives, still unlabeled data, still predicting next token. The only thing that has changed, and I will read it here, focused curriculum or reasoning-heavy data to deepen capabilities. And I'm going to go to my slide, which has a screenshot from their paper for a second. So here you can see how the data is mostly web here. And in mid-training, you see how code, math, reasoning kind of becomes a little bit boosted there. It's still pre-training. You're not using human responses. You're just using scientific data, GitHub code bases and things like that. You can still do the next token prediction and those. And this curriculum like this had been motivated by what the community cares about right now. So reasoning is all the rage. So this is why the curriculum in this mid-training is focused on coding and math, right? If we had all collectively suddenly cared about something else, we would, change these mid-training to be on something else, right? Okay, so that's, I would welcome you to think about pre-training and mid-training as just pre-training, where at the end of the pre-training, you are smart about which data you are presenting, because you know that later stages are more important. And there you are going to, at the end of the pre-training, put the data you care about, which is, of course, you're not going to be making this decision alone. If you are in a pre-training thing, you're going to be making it with your whole team, and you're going to be spending millions of dollars. So, right. So this is not a choice you personally will have, but your team at best. So that has changed. And then also in this pre-training stage, they are going to have, in the final stages, they're going to prepare their model to be better at processing very long sequences. I hope you remember when I told you that training with long sequences is computationally expensive. And anyone remember why is it expensive? Yep.
It's quadratic.
Exactly, it's quadratic in a sequence length, and what we mean by quadratic in sequence length is attention mechanism is quadratic in a sequence length. So you have this gigantic attention matrices where you need to store, you know, if you had 100,000, that is the sequence length, then square of that as a number of numbers you need to place in just a single attention matrix. Okay, what exactly is the resource that we are lacking to place such huge matrices? GPU memory, right? So GPU memory is bounded, and to put all these numbers in a nice float precision, we just don't have it, right? So we are bounded by what you can do, and then also why the performance degrades is row. We said that the positional encoding we are going to use is row, and row, if you show longer sequences than what there are in the training, the model will fall. So we know, okay, long context, people just want to put a lot of things in long-term context. Think about code, code if you're using it. It has this massive memory with all the code, like your code base, and it's all history and everything you have prompted the model with. So because this is computationally expensive, they're going to start training with shorter sequences, and then at the end, they're going to train with long sequences of 60,000 or more tokens. Now, here you'll see there are two different branches. There is this branch, forget about this one, and this one. Both of them are going to have thinking SFT, which is now supervised fine-tuning for long chain of thought reasoning. The reason why long chain of thoughts are important is because it has been observed that if you give a lot of compute to the model to generate lots of tokens, eventually it will come to some right answer. And this is referred as test time or inference time scaling, letting the model generate for a long time until it comes to make sense of what it's saying. You know how I just moments ago said, oh, I'm rambling, I'm changing my mind, and now I'm thinking this and that. Basically, that's what these models are doing now. They're kind of having compute to generate these tokens and to generate until they make sense of what's going on, like as if they're having some kind of sheet of paper they're working on. And then by having that people, opportunity, they are usually better at answering complex stuff. So long chain of thoughts are what is going to be introduced here. And now there are two different branches. This branch is basically what we have learned in this course. You start with instruction fine-tuning. Just to be clear, this was instruction fine-tuning as well, just the source of data was the data where you have long chain of thoughts. This data is just a mix of all the instruction fine-tuning stuff that we have learned already before. So here we are priming the model for chat behavior and instruction following. After that, there is alignment using, DPO, great. Something that has just released last week, or I don't know, this week I keep lost track of time, but DPO is still an algorithm for learning from preference data, and this is for refining style and tone, right? Harmlesses. And now, even here, we do care because that's kind of what the community cares about, is this math and coding abilities. So there is going to be one last stage I haven't teach you about, which is reinforcement learning with verifiable reports using GRPO for math, coding, and other stuff. I'm gonna come to it in the next slide, but hold on thinking about that for a second. This other branch is going to be used to create the thinking version of the model. So today you will see your model comes in flavors of, this is your regular old pre-trained model. There is a chat version of the model, which they call here instruct. So today instruct usually refers to a chat version. And just SFT is not even released because no one cares just about SFT. And then you will have this thinking model. So all the open model and famous of model like Quen and Kimi and all model, they are going to come with chat and thinking version. And then OpenAI has its all one family of model. And then now with ChatGPT, you can click either instant or thinking. Okay, so basically what I want to say in terms of what you have learned, not significantly much has changed. It's rather about the data, right? Like we embrace this fact that what you add at the end of the curriculum is remembered by the model more. So if you care about your model being great at math and code and science, you add that kind of the data at the end of the training. If you care about the model having ability to produce long thinking traces, you add that data at the end. If you care about long sequences, your data has to have long sequences, right? So it's all about what kind of data you add and where, but you still have your pre-training, SFT, we have DPO, and now this extra reinforcement learning with verifiable rewards I will mention. Before we go, I won't talk too much about what reinforcement learning with verifiable rewards is, but do you have any questions before we move forward? Okay, so as I said, today we have these 3 stages as I mentioned, but we also have mid-training. Everything is kind of now done such that we lay groundwork for instruction and thinking capabilities in these post-training stages. So we have mid-training where we have targeted data curation for code and math. We have long sequences, and then we have long chain of nodes. We have this thing that's now super important, inference or test time scale. The idea that if you give more computational resources, which are, think about them as number of decoding steps, more decoding steps you allow to a model during inference, you're going to improve their quality and its reasoning tasks. And then comes final stage, which is this reinforcement learning with verifiable rewards. So we have used DPO, as I said, which doesn't have a reward model anymore. So now why reward model again? Important thing here is that these verifiable rewards, as name says, they are something you can verify, right? Unlike when you need to, for example, here is an example of something that's not verifiable. Explain the moon landing to a 6-year-old in a few sentences. What makes a good 6-sentence summary here is somewhat subjective, right? So we don't have this objective reward that we can just give to this response. Rather, we need these rewards that we have learned in the last lecture. On the other hand, with math, you can have correct answer. There is just a single correct answer. It's objective. There is no discussion about it. So you can just say, hey, did you get the right answer or you not? Similarly, with coding, we have compilers, right? So why can't we just compile some unit tests and see whether the code works, right? And then if it works, we give the reward, and if not, we don't, right? So verifiable rewards are different from rewards we were talking about when we were talking about harmlessness, because they are objective and you can verify them, and you don't even need trained models for verifying. So in this RLVR state, when we use these verifiable rewards, we would actually use something like rule-based system for math. You would use some kind of code compiler unit test-based thing for coding reward. And for some of this instruction fine-tuning stuff, you can use some kind of constraints and then see whether the model satisfies the constraints, which is also somehow rule-based reward. So we don't actually train reward models here with this last stage. Rather, we use some of these, kind of verifiable things. And GRPO is an algorithm for training models with these rewards. It is built, I'll just give you a high level intuition of how it works. It basically generates responses from the model. Each one of these responses gets certain reward. Then you calculate what is the average reward across all of these responses. And then you promote the probability of the response that's above average. And otherwise you don't promote the probability of other ones. That's the idea behind GRPO. You can imagine there is some loss function that we derive from this intuition, and then we use that loss function to do this final stage of tuning the model. As you can see, GRPO has been released just last year in DeepSeek R1. It's still something that people use with additional tricks, right? So we are coming into very, very new territory. However, I want to emphasize something. My community a little bit crazy about reasoning models because, as I said, it's challenging, unsolved, fun new thing to work on. Do we now all need to use reasoning language models? We don't. Actually, most of you will be better off of not using them. They are very slow. If you have, Pro or whatever they are called, plus versions of ChatGPT, and if you're using Thinking or Claude Sonnet 4.5 these days, super slow, right? Like they're just waiting and waiting. And there are maybe some tasks where waiting is, pays off. But for most of your tasks, like summarization, translation, knowledge-based question answering, you don't need this thinking, right? So just a pure normal LLM with instruction fine-tuning and DPO will be enough. So just watch out that you don't fall into this trap, okay? Because this is hottest new thing that you need to use them. For most NLP applications you want, but there are still NLP applications where you do need heavy reasoning. One example is differential diagnosis. It's a task where a clinician needs to take into consideration your current symptoms and then decide, oh, should I ask them more symptoms? I have these options for what could be going on with this person. Should I order some tests maybe and get more, observations, maybe immediately start to treat them? There's like a lot of moving pieces. And, once let's say more tests are done, more information comes into play, clinician revises their reasoning and then eliminates some diagnosis and so on. And it's an iterative process. So that's an example if you would like to do this with an AI assisted way. So you have an NLP LLM-based model that is looking into patient's clinical note and it's supporting the model in this iterative way. Then I think some additional thinking might be beneficial. So not to say no NLP application has, wouldn't benefit from reasoning language models, but a lot of them don't. Okay, let me go over this. So you need to know what these things refer to. So there is a base, instruct, chat, and thinking version of the model. And I have already said base model will always be the model that's produced by pre-training and pre-training alone. So no human label data input. Now, this is where things are going to get confusing. Instruct and chat versions, depending whether the model was produced in 2024 or 2025, they might refer to different things. So in 2023, 2024, we referred the instruct version of the model to be SFT only model. But today in 2025, it also often refers to SFT and aligned using DPO or RLGF. So you need to be cautious there. Chat will always include the RLGF or DPO aligned model. And then thinking or reasoning, as we have just seen with ALMA 3 as a case, will have pre-training and then extra advances to make it, better for reasoning, like mid-training the long COTs, long sequences. And then there will be finally that stage where you do have the not RLHF, but reinforcement learning with verifiable, using usually GRPO. So just put, watch out for that. I don't rely on my memory. So when I open a Hugging Face page of a model, I read a little description that says what it was trained for, and it's going to specify whether it's just instruction fine tuning or also includes DPO. And then thinking will almost always be the name of the model itself. Okay, so we're going to stop here next time and see how excited I got. I have a lot of time, and then again, I didn't finish everything I want to say, but what I want to kind of talk about is just like there are so many options what to do when you have a new class. And then we are going to also talk about how to do your fine-tuning of your model in a more efficient way, and how to use the model in a more efficient way because they're bounded by the CPU memory. This is going to be the very last topics we are going to talk about related to elements, but very important in practice. Okay, see you on Wednesday.